Hi, welcome to the CMS Summit. My name is Oscar Pinto, and today I'm going to talk about SNIA CS APIs as a programming guide. So today in our agenda, we have, we're going to talk about the SNIA CS APIs by themselves. We are going to talk about the programming usage, how they may be applied. We'll use an example and walk step by step until you use them. We also will give a progress update on what is happening on the specification, and then we'll end this with a quick summary. So what is Computational Storage APIs and what is the work that we're doing within SNIA? So let's use this figure on the left, on the right, that from the bottom that shows how a device may be used with the SNIA CS API library. So we have a computational storage device, a drive is shown here that has some storage, has some device memory, has a computational storage engine that runs a computational storage function, CSF. And here are several examples, and they may be implemented in software or hardware. It totally depends on what the manufacturer has provided as part of this computational storage device. Examples would be, it could be in ASIC form, it could be in CPU form, it could be an FPGA, and so forth. Now the device is connected to the host through a device driver, and the device driver knows how to talk to your device. And the device driver helps you connect to your SNIA CS API library. Now the API library is connected through a thin layer of what we call as plugins. The plugins basically help you connect your abstracted CS APIs to your specific device stack. And your device stack could be any implementation. So at a high level, the APIs, they are kind of abstracted. They can work across devices. And because they're abstracted, they can hide your device-specific details on your hardware, your connectivity, and how the device may have been implemented. So the vendor-specific implementations are totally hidden because of the abstraction. The abstraction also hides through the interface how the device may be discovered. And so it provides a standard set of interfaces for discovery, for access, on how memory on the device may be allocated, and how data may be transferred to that device memory, either from storage or from host memory, and vice versa, and how these compute functions may be executed or may be downloaded if the host application, the host user has their own compute function. Also, the total management of this is provided through this interface. Now, this interface is extensible because you use one set of APIs using this plugin interface, and this plugin is the magic that maps it from the abstraction to your device-specific implementation. Also, we have kept these APIs as abstract as possible, that they could be implemented on any APIs. That is, they are agnostic to your specific OS implementation. From your programming perspective, we have two programming modes, basically your privileged mode operations and non-privileged mode operations. So privileged mode is basically for as an administrative task, wherein you would go ahead and configure your compute resources, be it your device memory and so forth, your compute and so forth. You may also choose to download the CSFs, your compute functions, to your device and configure them, and also basic management of your device. Now, like I said, these are administrative tasks. We won't touch on this today. I have already covered this in a previous SNIA session at SDC last year. For non-privileged mode, which is for the majority of the application users that are going to use computational storage devices, you would have mechanisms to discover the CSX. You have mechanisms to discover the CSF, allocate device memory, execute CSFs, and then transfer data from storage into that device memory, or from device memory into host memory, and vice versa. So we will cover the non-privileged mode operations today. So let's get down to how the APIs may be used for the non-privileged users or normal users. We will use an example here. So this example is using a data filter. For simplicity, let's say the data that we're going to work on using this data filter on the computational storage drive is animal data, so a list of animals that are there on the device. We will allocate some memory and load the data from storage, the animal data, and then we will run the data filter, the simplistic filter that filters out cats. So basically it's a cat filter. And then once the filter is run, we will copy the results of the cats that were discovered back to the host. So APIs have two sets of steps to run. The first one is your setup, and the second one is basically running your computational storage IOs. So 3 steps for setup, 3 steps for IOs. So very minimal steps, and we'll apply these 6 steps for this example that we just talked about. So the first 3 steps are for setups. The first one is discover. So wherein you go ahead and discover your computational storage device. And once you discover the device, you would go ahead and discover your computational storage function. And then you would go and allocate some device memory. And once you have completed these 3 steps, you are ready with your setup and you are ready to perform your computational storage IO. But first, let's get down to each of these steps. So discovering a CSX. So we have an API called get CSX from path, wherein you provide the path to your storage. And the outcome of it is that API will go and find out the nearest compute available for that storage path. Now, we are talking about computational storage devices, and the API will take care of all the compute that is available for that storage path and present you with the compute devices. Once you have a list of compute devices, in our case, it'll just be one, you would go ahead and get access to the right one, and the outcome of that would be a device handle. So for that, you would use open CSX. Once you have discovered your CSX, you would discover your CSF, your function. And for that, we use the API get CSF ID. Here, you provide the device handle you got from your previous step, and you would specify the filter. The CSF here is the filter that you want to get access to. And the outcome of this is one or more CSF infos. And the count here specifies if there is more than one, you would walk that list and find out which is the best one you want to use. Now, CSF info is a list of data structures, CSF ID info, and they contain information on the actual CSF and the additional information on the relative performance of that CSF and the power it may consume. So if you may have a requirement of the most performance CSF, then you would pick up, as this example shows, the most relative performance. But if you have the requirement of to use the least amount of power because the device has that capability, you would pick up the one with the least amount, the one that uses the least amount of power. So once you have covered the step, the next step would be you would go and allocate device memory, that is allocate FDM. So for that, the previous the CSF info structure also contains information on the memory that function has access to, because that function runs on compute, and compute needs access to device memory. So here, that list of device memories or the memory pools are come along with each CSF. So you walk that list again, like shown in the previous step, and pick up the most performant one, that is maybe that's the nearest one to that compute function. So once you have picked that up, you would use CSAllocMem as your the API. You provide the device handle, and you specify mem flags. For mem flags, you would specify the FDM that you just chose here, and you would allocate the memory. So the outcome of it is a memory handle, that is the AFDM mem handle. So once you've done that, you've completed your setup, and next stage you're ready to run your computational storage I/O. So again, 3 steps: load storage data, execute the CSF, and copy results. With this next 3 steps, you are done with computational storage I/O. So let's walk through each of these steps and see how we can go about it. So step 4 is loading storage data. So for that, we use queue storage request as your API. It takes as input your storage request. The storage request may be built using file information as shown here, a file system, a file handle, an offset to that file, and the amount of bytes you want to read from that file. Or you could specify by LBA, and this is extensible. We are still working on it. It could be extended to KV, object, and so forth in the future. Now, this API by itself, it starts with CSQ, a star request, and we follow the same format for the next 3 steps. So the input is the request. The next one is the context. Here, the next 2 parameters are shown as null, which means this API is working in synchronous mode. But if you so choose to use it in asynchronous mode, then you may specify a callback for the 3rd parameter or an event for the 4th parameter. So you have these 3 options as completions. And the next parameter is a pointer to if you want to cancel this I/O in the future. And the last parameter here is when this API completes, it can return up to a 64-bit completion value, plus any results and any additional data buffers that may be passed down to the compute later on. So this is your queue storage request. So in step 5, now you're ready to execute your compute request. So you loaded data previously, and now you're going to go and run your data filter, that is your CAT filter. So CSQ compute request is your API. It has 3 parameters. Here you specify your filter function ID, and then your 3 parameters, basically your input buffer, which contains the data you previously loaded from storage, that is your animal data, and the length of the data that is populated, that is the data that you just read, and then an output buffer, which is a second handle to your device memory. And like I said, it could be done in synchronous as well as in asynchronous mode. And once it completes, you have, if successful, you will get back the results of your data filter, which is all the cats that are available in that animal database. So once you have that, the next step would be you want to copy that data from device memory to host memory, because that data is still residing on the device, because the compute ran on the device and the compute works with device memory. So here we have CSQ copy mem request as your next API, for which you specify the direction. So here the direction is copy from the device, and you specify where that information wants to go. So that is into host memory. You provide your host memory address, and then you specify the results buffer, which is in this AFDM handle 2, and from what offset, and the number of bytes you want to copy. It can be used in synchronous as well as asynchronous mode, like the other 2 APIs. So with that, we covered how to use computational storage APIs for non-privileged users. To summarize, we just need 6 steps, and those 6 steps are shown here now in API form. So here are all the APIs that you need to run computational storage using the SNIA CS API libraries. Again, you only need 6 steps. So with that, let's look at progress. What are we doing from the specification front? So last year, we released a 0.8 of the specification, for public review, and that is available, still available for your review. But since that specification, we have made some advances, and those have been from that storage request. We have advanced that storage request to now take LBA ranges. Now, these LBA ranges are most beneficial if your data is fragmented or your data has data and metadata as inputs. And you can specify that in LBA ranges. Also, if your data is managed by your own file system, then using LBAs and using in this way seems to be most desirable. We also made advances on device memory. That is, a device manufacturer may provide a device with more than one device memory, and that device memory may be based on most performant to least performant, or most accessible to least accessible, and that may be because it has more than one compute, and so forth. And we also made additions to how you may abort a request, how you may cancel a request, and also reset, and so forth. We made additions to the compute functions, that is how you may handle the compute functions. We extended that further. We added something called global identifiers. And now this may be covered in other sessions, but basically a global identifier is a standardized way of identifying a function. Now let's take that cat filter that or the data filter that we had in the example. So let's say we want to use this data filter not only on vendor A, but also on vendor B and so forth. So that is a standardization at the identifier level. So we have one identifier, global identifier, that if you specify that, then a user may be able to run that same function on any vendor's device because it has the same inputs and the same outputs. It may be implemented differently, but you can get the same outcome. Also, the global identifier is good when the same function may be implemented in different compute forms, that is CPU, FPGA, and so forth. So we are making advancements on that separately, but the compute function takes care of addressing that. We are also making sure that all the API work closely aligns with NVMe. So we're also working closely with NVMe to make sure these work together. So with that, let's summarize on what we covered today. So we have the SNIA CS APIs. It's a very simplified interface. Like I said, we just needed 6 steps to do all the operations for computational storage. So it's a simplified interface, and these APIs can map to different types of device solutions, computational storage device solutions, because they're highly abstracted. They don't basically get down to the device details. They're simple to follow and scalable because you could be attached locally or remotely, and that actual implementation is hidden beneath the layers using the plugin interface and so forth. And likewise, they have very minimal steps to adopt. And that's it. That's all I had for today. Now, there is some additional sessions that on computational storage from SNIA side. Please follow these so you get a broader idea on what else is happening on the standardization on computational storage. So we have one from SNIA, and there's also one from the NVMe side on how all this fits together. There are also other sessions from other esteemed SNIA members on computational storage. Please have a look at that and see how computational storage may apply to your organization and so forth. If you're interested, please join our efforts on standardization. So we have work that is going on in SNIA as well as in NVMe. Also help us build our ecosystem. Thank you. Please rate my session, and that's all I have. Bye-bye.